Hi.
Hi, hi.
Hi. It is Gabriel. I am happy to be here.
Hello, colleagues. How are you?
Hi.
Gabriel, may I ask you if you are my co-host or I am your co-host?
You are the chairman. I am only the co-chairman. So
I don't know if that says it. I'm happy being a co.
no, you are not the co. I am the co.
All right.
The difference is that you have to open the session.
And ask all the questions too.
Yes, exactly.
Right.
So may I ask whoever's hosting could put on the screen sharing so I could put my slides up.
The host is goes by the name admin. I don't know who is that.
So now it's available.
Okay, thank you.
Sorry by delay.
And just check so I don't have the same problem that Sergey had before. Is it changing?
Yes, it works.
It's
Good.
okay.
Thank you.
Two p.m. Let's start.
Thank you, Madam Chairwoman. Michael, you can hear us? Something is happening. All right, we have healthy 25 participants, I can see, and it is my great pleasure to invite everyone to the next session of our conference. We have exciting line of talks, and the first talk is by Professor Mark Dennis from United Kingdom with the talk of isotropic random electromagnetic waves, revisited optical currents and 3D zeros Mark, the floor is yours.
Thank you, Anton, and hopefully people can see my slides there. So it's a great pleasure to be talking to you all from the University of Birmingham. We're very proud that our first professor of physics in Birmingham was John Henry Poynting. You can see this is a blue plaque from our physics department. Perhaps not because of him determining the mass of the Earth, but of course because the Poynting vector is the current vector for momentum flow in optical fields, which is so important for both correlation optics and singular optics. Before I get into full flow, I just have to put up a quick advert for our graduate center. So this is the Center for Doctoral Training in Topological Design at the University of Birmingham, that's not just in optics and photonics, but in a huge area of topics involving quantum technology, soft matter, engineering and fabrication. And so we do have some fully funded PhD places still open for 2023 entry. So if you know anybody who's looking for a PhD in a topological type area, please get in touch with me as soon as possible. So what I want to talk about today is a model that has been around for some time. I remember talking about the model at the Correlation Optics Conference way back in 1999, but we've been looking at it recently in regard to some particular features, and I think it's been a little bit counterintuitive and surprising. So I want to share those results with you, as well as promoting this model as a very interesting one for thinking about, let's say, correlation and singular optics. And so I'm calling it this monochromatic isotropic random vector field. So the idea is that in this model, it's a superposition of plane waves in 3 dimensions. So the plane waves are have got directions on a sphere, and each plane wave has got a random amplitude, phase, and carries a random polarization. So this is truly random in 3 dimensions. It's a sort of generalization of the scalar models that we talk about quite a lot. So this is a visualization of what this looks like in an 1/8 of a cubic wavelength, the λ/2 cube. And you can see that there are ellipses everywhere, but because the k vectors are traveling in all directions, the ellipses can be oriented in all directions as well. So it's like regular optics, but not beam optics, because we don't have a transverse direction. So I like to think of this as monochromatic ambient light. In a sense, the electric field has made up of ellipses. The ellipses are randomly distributed with random phase, random shape, random size, and a random azimuth, but now also a random plane. The orientation plane of the ellipses changes with position. And I believe Miguel Alonso in his talk tomorrow is going to describe a little bit about how you might define Stokes parameters in fields like this, because obviously we're not transverse. We've got to include the Z or Z component. So let's think about the sorts of structures in this field. So it's a bit like a speckle field. But when we normally think of optical speckle or random polarization, we're thinking about a beam. So the k vectors are all almost traveling in the Z direction. So this is random, but as I say, it's equally traveling in all directions. So maybe a better picture to have is to think about something like black body radiation or the cosmic microwave background, where the k vectors are coming in all directions. But in those cases, I wouldn't call it optics, because the distribution of the wavelengths or the frequencies isn't monochromatic. It actually, in these cases, follows the Planck spectrum. And so we don't really have ellipses, as Konstantin was saying this morning. The pattern is slowly changing with time. But when it's monochromatic, we have this well-defined ellipses and phases everywhere. So it's something in between black body radiation and a speckle pattern. But it's, as I say, we've got a lot of the tools that we're describing in this conference are useful for describing this model. So the two things I want to really talk about today are in these two papers. One with Titwan Gadain, who's just finished an internship in my group. And we just put it on the archive last week, where we're looking at optical momentum distributions or optical currents in this model. And then the other working with the group, with a PhD student of Paco Rodriguez Fortunio in King's College, where we're asking a slightly different question from normal, not what is typical in these fields, but if we go a little bit further and place a nodal point into one of these fields, what happens nearby? So it's a sort of generalization of our usual singularities, that we're fixing this point as a special boundary condition. So I'll start by talking a little bit more about this model. I'll talk about the pointing vector and its decomposition into spin and orbital currents. Then I'll talk about how these currents are distributed in this particular model, and some of the perhaps counterintuitive properties they have. And then I'll talk about structure of nodal points in the random vector fields. But first go to the isotropic random monochromatic model. So I've already talked about it. It's one of the things that's very nice about it, as with speckle patterns, because we're adding together a lot of identically distributed random waves together, we can actually treat them as Gaussian random functions and do statistics analytically. So it's not just numerics, we can actually do analytic statistics with these distributions, at least if we're lucky. Also, with the fact it's monochromatic, there are no free parameters except for the wavelength itself. So we're not tuning lots of things. It really is a sort of universal physical model. And as I say, to my knowledge, the first time it was used really systematically in this field was Michael Berry and I, in work I talked about 24 years ago in this conference, is the distribution of polarization singularities in 3 dimensions. So Konstantin Bloch talked a little bit about polarization singularities this morning. They're distributed randomly in these, and we were able to calculate the analytic densities. Michael, together with Pragya Shukla, a couple of years ago, returned to the model to consider the issue of local wave vectors and natural superoscillations in the field, which are related to currents, but not quite what I'm going to be talking about, which is, as I say, just this work that we've just submitted now. There may be other examples of analytic statistics I've done in this model. Please let me know if you know of them, because I think I'm trying to build up a catalogue of what's known in this model to try to see whether we can try to understand things better. I mentioned already an analog that we're very familiar with is the monochromatic scalar waves. So now we've got scalar waves which just have an amplitude and phase, but traveling in all directions in 3 dimensions. And it's been well established both, theoretically and experimentally, that in these cases, there's a dense tangle of optical vortices where the phase isn't defined in these systems in 3 dimensions. In fact, the analytic density is 4 pi over 3 lambda squared length per unit volume. And if you think about that within a cubic volume, there's quite some length of vortex typically in there. So the vortices in this tangle, they can be loops, and if they're loops, they can be both linked and knotted. So it's quite complicated topologies can show up, and then structure around them, such as the ellipticity of the core, the vortex. Again, matches the observations, and the numerics match the theory very, very closely. So that's sort of what they look like, characterized in terms of singularities. What about the current distribution? Well, for a scalar, there's only one scalar current, as Konstantin mentioned this morning, and this is the probability density function, the probability distribution of the length of the current vector. It can be quite large fluctuations, but it's normally quite small. Of course, just looking at the probability distribution doesn't give you a picture of what happens in the fields. Here's a simulation, slightly old, from the group in Sweden, and you can see these are the vortex lines, and here you can see one of the streamlines of the current. It wraps around one of the vortex lines quite tightly, and that seems to be quite typical. The current lines, they move around until they get close to a vortex, then they wind around quite tightly. Here's a picture of the that tries to capture what's happening using 2-point correlation function. So the J here, you can see, so this is looking at the correlation of J for a vertical vector or y-directed vector. It tends to oscillate perpendicular but follow the same path parallel. And so this statistics captures the sort of what the in-plane streamlines are doing. So blue is when they're pointing slightly down, red is when they're pointing slightly up, and you can see that they're fluctuating, but there are some sort of tight little vortices, as well as some areas of quite consistent flow. Now, if we wanted to measure the current, one of the problems is we don't measure it at a point, we measure it with a probe with a finite size. So to capture that, what we've done here is we've convolved the pattern over a disk of diameter lambda. So this is insensitive to structure smaller than a wavelength. And you can see a lot of that structure, particularly the vortices, gets washed away, but what we end up seeing are the strong, consistent bits of flow direction. So these are the smoothed in-plane streamlines. So that's just a picture of what the current is doing. Here a little bit sort of qualitatively in 3 dimensions, and here a little bit more quantitatively in a 2-dimensional section. For our random polarization fields, we don't have vortices. We've got lines along which the polarization is circular, as Konstantin was saying, and lines along which the polarization is linear. And then in planes nearby, the ellipses are almost circular and almost all in the plane, or the ellipses are almost all perpendicular and almost all linear. So people tend to prefer talking about C lines to L lines. So that's what I'm doing here, that there are different classifications of C lines depending upon the structure of the ellipses nearby, in particular these directrices that pick up the direction of the major axis. And the point really here is that there are discrete classifications of C point depending upon what this distribution looks like. This is in the plane of the ellipses. Out of the plane of the ellipses, there's some variation as well. And the way that these two combine and interlace gives the Mobius bands that Konstantin was talking about. But again, the important point here is there are different types of Mobius bands, typically with different numbers of twists, and that depends on the fact that there are these discrete families that the singularities fall into at each point along these lines. Okay, so now to talk about the pointing vector. So again, I'm taking the advantage of the fact I'm assuming things are monochromatic, and in a monochromatic field, it's natural to take the time average pointing vector. So that's half of the real part of E star cross B. And we can rewrite B in terms of E using Maxwell's equations. I'm not going to go through the details. I'm just going to say that the pointing vector P can be written as the sum of the so-called orbital current term, where it's like the inner product, like a quantum mechanical inner product of the components of E, taking as a sort of expectation value around this gradient, or using this more compact notation with the gradient in the bracket, due to Michael Perry. And here's a spin current, which looks different, slightly different. E star cross E, or imaginary part of E star cross E, is the spin perpendicular to the ellipse, and so this is the curl of the polarization ellipse spin. And you take the sum of these two terms, we get the standard Poynting vector. Take it and so this is a historical decomposition that I think was first done by Belinfante, but for a general electromagnetic field. In Belinfante's case, he found that it's actually a gauge-dependent decomposition, but when the field is monochromatic, we lose the gauge dependence and it becomes a unique decomposition. So yet another reason to focus on monochromatic optics, where then this separation is completely unambiguous. So properties of the orbital current, so it goes in the direction of a plane wave's wave vector, and for a plane wave it's insensitive to what the polarization is doing. In field theoretic sense, it's the canonical momentum of the field, and it's the term that's responsible for radiation forces. So this is quite often what people will actually think of as the most meaningful optical momentum. And also, whereas the spin or Belinfante current, it's this curl of the ellipse normal. It depends on the polarization or the spatial change of the polarization. You can think of it as a geometric phase correction to the canonical expression to get the real expression. But normally in beam optics, polarization doesn't change too much across the beam. And so in general, the spin current is a lot smaller than the orbital current. That's the sort of paradigm that we normally think, that the orbital current is pretty similar to the Poynting vector in a lot of cases. Here's an example of explicit system where they both come up, that was proposed by Konstantin Blyoch, Alexander Bekshaev, and Franco Nori a few years ago, and was experimentally realized by Massimo Antognozzi and his group in Bristol a couple of years later. So this is looking at total internal reflection of a circularly polarized plane wave. And in the evanescent field, it turns out the canonical momentum points in the direction of the K vector following this direction, but the spin momentum is perpendicular and points either to the left or the right, depending upon the handedness of the circular polarization. So this is a real way where the two ones are completely separated. Of course, the Poynting vector is the sum of both of them. And so even in this case, so the force on a particle is a lot larger from the canonical momentum than from the spin momentum, although it's perpendicular. And in this experiment, they were able to make the measurement but using a cantilever that just has 1 degree of freedom, and so could only move in the direction of the spin rather than the orbital momentum. And this was the measurement. It was quite a complex experiment, but nevertheless can be seen as a strong evidence of a measurement of the spin momentum. Was, as I say, I think in this case was 2 orders of magnitude approximately smaller than the canonical momentum. So let's go to our 3-dimensional isotropic picture and ask, what are the distributions? What are the probability distributions of these 2 sorts of momenta? In this case now, where we're really thinking about varying position-dependent polarization ellipses, that we're not in the beam regime at all. And it's worth pointing out that we can also write the 2 momenta in an alternative form involving the real and imaginary parts of the complex E vector, where here with the orbital part, the P and the Q have got like this inner product. We're taking the inner product of the components of P with Q, and then we've got the gradient in between. Whereas with the spin part, the inner product is between P and a gradient. And doing the calculation for this, it turns out that the probability distribution at a point of these two types of current turns out to be identical. At a single point, the orbital and the spin parts are distributed completely the same. You can't tell the difference. The sum of them gives the pointing vector. That's a little bit different. That's the pointing vector distribution. Compare with the scalar current distribution we had before, very similar. Slightly more complicated in the case of these two, of the orbital and the spin, but the point is they have the same distribution. So I think it's fair to say that based on our regular experience from beam optics, that it's quite surprising that they look exactly the same. In particular, as I emphasize, it's normally quite hard to measure the spin current, whereas we can normally see the orbital current. But in terms of actually vector distribution, it's equal. As I say, they're distributed probabilistically exactly the same in this isotropic model. These are some numerical statistics, harder to do the analytics, but I think it's still pretty convincing. So this is now the probability distribution of the angle between, so the gray is the angle between the orbital and the spin current. And you can see it's quite broadly distributed, but centered on pion 2. So they tend to be perpendicular if they're at anything. And here they have the angle between the pointing vector in each of them, again, is statistically, you can see, is equivalent. They tend to be a lot closer oriented, this small here, because, sorry, you're asking a question? I'll keep going. So it tends to be, because when PO or PS is large, it will tend to be quite correlated with the direction of P itself. But the point is, they most likely themselves to be perpendicular. And here's a typical example of typical sample function where you can see the P is the black vector, the PO is the red, and PS is blue. Hopefully you can see there, they tend to be quite different. And here are the flow lines of each of the three seeded in the center of this lambda over 2 cube. And you can see, at least in this example, the flows are almost perpendicular. So you can see that actually the flow of the pointing vector in this model is quite different from what the orbital current and the spin current are doing. So are the orbital current and the spin current identical? Well, it turns out, no, the probability distribution at a point is identical, but as vector fields, they still look quite different. And the reason is, it comes from the fact that, again, if we're looking at 2-point spatial correlation functions, when we're looking at these vector fields, there are different sorts of correlations we can have. We can look at correlations of the components parallel to the displacement we're looking at, perpendicular to the displacement we're looking at, or different, or looking at different components. In fact, the different components, the correlations vanish. So the non-zero correlations are either when we're looking at the two components that are parallel to displacement or two components perpendicular to the displacement. And it turns out these parallel ones are a lot stronger than the perpendicular ones for this electric field. So when we look at these formulas, it turns out that when we're taking the dot product of the P with the Q, we're picking out the same components here, whereas the components here of P are being correlated with the derivatives in Q, not the components of Q themselves. So it would tend to pick out that PO is large compared to PS in terms of the correlations. So PO has stronger spatial correlations, or stronger positive spatial correlations. So here is a representation of it. And again, we looked at the J before. So you can see the PO, there's not much oscillation, whereas PS, there's a spatial oscillation going with changing sign, as we say, it's particularly when we're looking at the perpendicular component. PO, there's not much change of sign. The sum of them together gives us P, and P as a correlation function actually looks quite like J, a lot more like J than either of these two. So if we're taking a picture of look at the in-plane streamlines, it can see that there are the patches of correlated PO are a lot larger, and there's a far finer structure of the patches of PS. It's changing a lot more. The correlated the spatial correlation distance of the spin current is very small, whereas the spatial correlation distance of the orbital current is large. So looking then at the convolution again with a disk of diameter lambda, it means, because this structure is smaller than lambda, that almost all of the PS structure gets washed out, that you can't see it, whereas we see a lot of the PO structure at this length scale of a wavelength or larger. So when it comes to comparing with the pointing vector, it looks like the pointing vector is following a lot more the structure of the orbital current. That has the long range structure, whereas PS is a short scale modulation that we often miss if we're looking at structures that are, as I say, larger than the wavelength. So despite the fact that the two vectors have the same probability distribution, we still miss a lot of the PS structure unless we're looking at scales a lot shorter than a wavelength. So that's what I wanted to say about those currents, and hopefully find it interesting. And now, in my final few minutes, I just want to talk about the structure of nodal points in random vector fields, again, to try and give us a sort of intuition a little bit about what's going on with this ambient monochromatic model. So first, what we normally emphasize are the generic singular structures, the structures that are always there, and we just have to look for them. So in scalar fields, random scalar fields, we always find vortices, we find zeros, and a way of thinking about that is to say that if a complex number has a real and imaginary part, each of those are functions. The real part equals 0 is going to be a surface separating positive and negative volumes. Similarly, for the imaginary part, those surfaces cross where both of them are 0, and that's our vortex lines. Something very similar happens for C lines when we take the complex polarization scalar E dot E, as Konstantin mentioned earlier today. So the nodes of this phi correspond to circular polarization. And there are distinct kinds of C line, as we said before, that different classes of them, different Mobius indices. L lines are similar. P and Q must be parallel or anti-parallel, and that's two conditions as well, which gives us lines in 3 dimensions. Now, we could look at other structures. For example, if we were to evolve in time, have some slowly varying time, we could see them moving. We might see the lines reconnect, or small loops appear or vanish. And these are all typical things that we would expect in 4 dimensions. But to get the field to exactly vanish, that's six conditions. All of the 3 components of P and all of the 3 components of Q. So we expect to see that almost never in a natural field. All of these other structures naturally occur in these fields, but we have to actually put it in. We can put it in, but it's definitely something we would think of as a man-made. So we would say implanting nodal points in a random field. So everywhere else is just random. But at a point R0, we're going to put this these cold spot where E has to vanish. And it turns out that all of the structure of the cold spot, the nearby structure, can be understood by looking at this JE, this matrix, which is the matrix which is the derivatives of the E vector at the point. So what features do these points have generically? What do they look like in the fields? Well, one way of asking them is, well, clearly at a point where E is 0, the polarization scalar E dot E is 0. So it lies on, it's sort of trivially circularly polarized, but it's trivially linearly polarized. But what that means is that actually at these cold spots, we typically have one or more C line and one or more L lines crossing. So these are different possibilities. The green lines are the L lines and the purple lines are the C lines. It turns out that at one of the cold spots, it's a meeting of 0 to, it has to be a meeting of 0, 2, or 4 C lines, and the meeting of 1 or 3 L lines. And typically, if we're looking at what is allowed typically around such a point, that's it. So this is like the different classifications of the C lines themselves that we had, that there are these different numbers going through. And you might say, how can we understand that? Well, here's a justification for the C lines that Alex, the PhD student, came up with, which is very nice. So we've got this E dot E as this scalar that picks up circular polarization. And here's our point E equals 0. So if you think about it, the real part of E dot E is 0 on a cone going through this point, and the imaginary part of E dot E is 0 on a cone going through this point. Look it up in the paper if you want to see more details. So with these two sets of double cones, two sets of diabolos here, we've got different possibilities for crossings. The cones either don't cross at all, and that's the C point, because the C line is where the real and imaginary part of E dot E are both meet. They might meet once, so that would be they might meet twice with crossing once, or they might cross 4 times. And so this is the 0, 2, or 4 C lines. And there's a similar argument for 1 or 3 L lines through the point. So you can see that, again, we're using the similar arguments that what we often use in singular optics to try and understand the properties of these non-generic points. So you might ask, what does the pointing vector do? So the time average pointing vector, thinking of this as a monochromatic field, obviously there's no flux of the time average pointing vector at these points, they're just cold points. So it means that in terms of the real part of the pointing vector, they are a divergence-free saddle point. The imaginary part of E star cross B is the fluctuating part of the pointing vector. Turns out that is allowed to have a non-zero divergence, but not in all of the possible ways that you might think, because of the way that E cross B works. And this is a cold spot of E, not B. It turns out it can be a saddle or a sink, but not a source of the fluctuating part of the pointing vector. Looking at the orbital current, it turns out the orbital current tends to vanish on a line segment going through the point. And what that means is nearby then, the orbital current tends to be circulating around. So this is looking at various planes in YZ, so various planes in YZ, going through this sort of line segment where the orbital current tends to be along this line. And you can see that then means that there tends to be a strong circulation of orbital current at these cold spots. Whereas there's not much to say about the spin current. It is divergence-free, so it's going to be a divergence-free saddle like we saw before for the pointing vector, for the time average pointing vector. But it doesn't have this rotating structure. We don't quite understand why that should be there so much for the orbital current. So just to summarize, here are various different combinations of this J, this derivative of the E, real and imaginary, and its properties, its eigenvectors and eigenvalues, determine the various properties that we've been talking about: number of C lines going through, number of L lines going through, the index as a saddle point, and so on. So to conclude, we've described currents and singularities in this isotropic random monochromatic random vector waves, this ambient monochromatic light. And hopefully you see it's got quite some interesting properties. In this model, we've seen that the spin and orbital currents have the same probability distribution, but different correlation functions, where the orbital current is more coarse-grained and the spin current structure tends to be finer than lambda. We've introduced the idea of non-generic electric cold spots, and then these have which act as complicated organizing centers for C lines, L lines, and the current distribution. So thank you very much for your attention.
Thank you very much, Mark. Very nice talk. The floor is open for comments and suggestions and discussion. I can't see raised hands, so if you have yes, Miguel, please.
Hi. Very nice talk, Mark.
Hi, Miguel.
So I have a question on your slide where you talk about the angle between the two components, orbital and spin. There we just went.
Yeah, it's this one. Yeah.
So it's the gray thing. So it's
The
0,
gray, yeah.
0 and pi. So you say that it's more likely that are perpendicular than they are parallel or anti-parallel.
Okay, one has to be careful.
But I was wondering if this is not just telling us that there's no correlation between one and the other, because if you have one, it is more likely that you will be perpendicular than you're parallel, just because you have a great circle.
That's right. So that's true, but that doesn't. So you're right. They're uncorrelated. So what it means is they tend to be uncorrelated in direction, but being uncorrelated will mean probabilistically they're more likely to be perpendicular.
Okay, perfect. Thank you.
Yeah.
Okay, I can see raised hand by Oleg Yermakov, please.
Thank you for the very interesting talk. So maybe I missed the terminology. So when you show this orbital spin currents, optical currents, does it mean the transfer of energy together with the transferring of spin?
So it's a little bit more. So it's a little bit complicated. So the pointing vector has the dual role of being the momentum density and the energy flux, but it's the pointing vector itself that determines the flux of energy, and there's no separation to do with different sorts of energy. It's purely the pointing vector, whereas the momentum is a little bit more complicated because of this spin one nature of light.
Thank you.
All right, we have a bit of time for more questions or comments. Mark, can I ask you, I don't think you mentioned anything related to paraxial things, but I remember if we're talking about the scalar field and just optical vortices, the hunt for vortex knots and all that, I think it was abundant after a while, but is there anything I missed there in terms of statistics of?
No, so I should say it's something we haven't done and we intend to do, which is actually compute. So it's something missing from this story, which we've just not done, which is looking at the comparison of the spin and the orbital currents using the paraxial random model. Now we know that the orbital current has a very large Z component that would not be captured perfectly by the paraxial model. So we would definitely expect the spin current and the orbital current to come out quite differently, but we haven't, but it's not something that we've done yet.
All right, thanks very much. Guys, if you don't have any other questions, I would like to thank Mark for excellent talk and beautiful presentation. And we are ready to move to our next speaker. And that is Professor Alexander Bekshaev from Odessa with Bi-chromatic paraxial beam as a representative of spatio-temporal light fields. Professor Bekshaev?
Yes, I am. Do you see my slide?
No, not yet, and we don't see you, but we can hear you.
Now, do you see?
No, not yet.
I switch my screen on, but I cannot make the screen will be
Sorry,
seen for you.
we don't have the picture. You didn't share this screen with us yet.
Yes, it must go automatically.
Did you
I'm
click
not
on
sure.
share screen?
Yes, share screen. Is it?
Guys, if you had any such experience before, is there some tips that we can advise?
Normally, my screen was exposed without my participation. I don't know what I must do in this situation.
Well, you tried the share screen button because you see, it's not like you shared some other screen. You didn't share any.
Combination Alt plus S.
Alt S. Is now okay?
Yes.
Yes.
Excellent. Thank you so much. Yes, if you can go to presentation
sorry.
mode, that will be even better.
I'm sorry for my ignorance in this technique. Well,
Yes, it's all working. Thank you so much.
yes. Dear colleague, sorry for the delay. First of all, I would like to express my gratitude to the conference organizers who make such a titanic work and organized this conference that we can forget for a while about alarms, missiles, and all other scarce funding and other bad things. So, dear colleagues, spatio-temporal light fields attract growing attention during the past decades. This term unites mainly short pulses of structured light which possess a rich structure in spatial and temporal dimensions. Such fields are essentially non-monochromatic and have a wide temporal spectrum. That is, they contain a superposition of many monochromatic light components. The theory of monochromatic light beams is the best developed and forms the standard for the beam description. Therefore, it is tempting to reduce the spatio-temporal light field analysis to consideration of a limited number of composing monochromatic components. In this talk, I try to inspect such possibilities. how the important features and details of the spatial-temporal light behavior can be understood and characterized by considering a small discrete set of monochromatic components. Do you see any question? Monochromatic light components.
Your slides do not change. Can you move forward the slides? Can you try?
No. This is my introduction.
All right. Sorry.
Yes. Yeah. So we will consider a small discrete set of monochromatic components, and in the limit case containing only two frequencies. So we consider paraxial fields, where the physically selected longitudinal direction exists, along which the field spatial structure varies much slower than in the transverse direction. And the B sub 0 and Z sub R are the characteristic scales of spatial variations, and their ratio is the small parameter of paraxial approximation. In the simplest case of linear polarization, the field electric and magnetic vectors can be expressed through the scalar function, which in turn is expressed through the Fourier integral. Generally, the spectrum is continuous, even if there exists certain central frequency, and the main contribution are formed by the components which are close to this central frequency. Theoretically, the spectrum is non-limited. But we consider the simplest situation where the spectrum reduced to the set of only two frequencies, omega-1 and omega-2. So we consider the paraxial bichromatic superposition. In this case, the total field is a superposition of two monochromatic fields, and the electric and magnetic fields can be expressed in the following forms. Well, subscript 1 and 2 corresponds to first and second member of the composition. In the spirit of paraxial approximation, the complex valued fields E sub 1, E sub 2, and H sub 1, H sub 2 can be represented via the slowly varying complex amplitudes. These complex functions very slow spatial in comparison with this rapidly oscillating multiplier. The main characteristics of the field are the energy density and the energy flow density, which in paraxial fields are associated by simple relation. These quantities depend on time generally, but they contain time-independent terms and slowly varying terms, which oscillate with the difference frequency, as well as fast-varying terms, which oscillate with double frequencies and some frequencies. These rapidly oscillating terms are non-observable in real situations, so we will concentrate on the time-independent and slowly varying terms. In this slide, the expression, explicit expression for the energy density in the paraxial bichromatic superposition is presented. This energy density is associated with the longitudinal energy flow density. However, for spatial-temporal light fields, there is another important characteristic, so-called probability density or photon mass density. This characteristic immediately shows the distribution of the field matter. In monochromatic fields, the probability density coincides with the energy density, but in spatial-temporal light fields, their difference is obvious. Moreover, in general spatial-temporal light fields, the probability density is ill-defined in the coordinate space. And that is why its model even such a coarse model like here based on the bichromatic beam is maybe important and instructive. The single photon energy depends on the frequency, so the same energy corresponds to higher probability for lower energy photons and to lower probability of high energy photons. The probability density can be related to the wave function in the quantum sense, and this wave function can be associated with the electric field distribution and the wave number or frequency. Just about the same thing was said in this talk of Professor Blioch sometime before. In case of superposition, the two contributions, two wave functions, are linearly combined. As a result, we obtain the explicit expression for the probability density in the paraxial bichromatic model, which is similar to the energy density distribution, but it differs from it. These two expressions will be our main instruments in further consideration. As general characteristics of the energy density and probability density, in agreement with the usual practice, we consider the energy center and probability center. These are transverse coordinates of the energy center and of the probability center. As usually, they are defined as the mean weighted values with respect to the energy density and probability density. Now consider behavior of these characteristics for the model bichromatic beam. As a model beam, we take the superposition of Gaussian and Laguerre-Gaussian modes of the lowest orders. Propagation of each component is dictated by its own frequency. The beam radius and the wavefront curvature radius evolve according to the usual rules, where this quantity is the Rayleigh length for both for each component, for monochromatic component. These expressions give explicit expressions for the energy and the probability center positions. And these expressions, energy and probability center coordinates, appear to be rather similar and differ only by this denominator, which represents, in essence, the linear along the propagation direction density of the energy and the linear density of the probability. Now we proceed to some examples and start with the basic case of monochromatic beam, where both frequencies and both wave numbers are equal. Here are the numerical values taken for calculations. This wavelength approximately corresponds to the helium-neon laser radiation. This waist beam radius corresponds to the Rayleigh length of 10 centimeters. Then the distribution, here are the combined beam, this monochromatic beam, which is a combination of the Gaussian and Laguerre-Gaussian beam, is essentially three-dimensional and possesses asymmetric intensity profile. It can be better seen, its evolution with propagation is seen in this series of beam profiles taken at different propagation distances. In the coordinates normalized by the beam divergence, like here, the evolution of the beam profile looks simply as a rotation of the bright spot near the nominal propagation axis Z. And the whole rotation constitutes half pi on the full propagation length from the waist cross-section to the infinity. So the beam pattern is stationary and essentially three-dimensional. The energy center and probability center coincide here by the definition, and their behavior is presented here. With the beam propagation, the energy and probability center coordinates evolve linearly. This is horizontal coordinate, vertical coordinate, and also by the red line here, the behavior of the total displacement of the energy or probability center from the beam axis is shown. And this image shows how this looks when seen against the beam propagation. All these details are well known and reproduced here for further comparisons and discussions. The main distinction of the non-monochromatic superposition is that it behaves non-stationary. The beam structure shows a sort of periodicity both in spatial and in temporal dimensions, and it oscillates with the difference frequency.
You people can come if you want to join, Pranesh.
And oscillates along the longitudinal direction with the period dictated by the difference of wave numbers. So we can consider separately two simplified cases: the instantaneous spatial structure of the beam in a fixed moment of time, and the time-dependent behavior in a fixed cross-section. Now consider the instantaneous beam structure in a fixed moment of time. This instantaneous beam structure, as we have seen before, is longitudinally inhomogeneous, and if the coordinates normalized by the beam divergence, this instantaneous structure looks as a helical spiralic structure, which with the period dictated by the wave number difference. This figure demonstrates the evolution of this beam pattern in the normalized coordinates with the propagation distance, and it shows a simple rotation. And this rotation is clockwise when this delta k is positive. Here, the evolution of the energy center and probability center is illustrated for different spectral width or different frequency differences. This, we can see that the coordinates of the energy and probability center oscillate, and this oscillation amplitude grows according to the beam divergence. The oscillation period is inversely proportional to the frequency or wave number differences. When seen against the beam propagation, this evolution looks as a spiral migration of the energy or probability center, and the spiral evolves in agreement with the beam divergence. The number of coils and the period of spiral is associated with the period of energy and probability center oscillations. In both cases considered in this slide, the difference between the energy center and probability center position cannot be seen. Visually, it's very small. Now we pay attention to the beam temporal behavior in a fixed cross-section. We see that the beam profile rotates, but now this rotation is counterclockwise for positive angular velocity, for positive frequency difference. Together with the fact that the beam profile rotates with the motion again along the propagation distance, this enables to classify such beams as rotating beams. But there is a specific flying section in this rotating beam where the beam profile looks more stationary. This flying section moves with the light velocity. Strictly speaking, the beam intensity distribution in this flying section is not absolutely stationary and evolves a bit, but much slower, approximately like in the monochromatic beam. It is this flying section which represents certain features of propagating spatio-temporal wave packets. And for this reason, we consider its properties in more detail. Of course, like before, we concentrate on the behavior of the energy and probability center. And again, in all considered situations, the difference between the energy and probability coordinates is imperceptible. While the frequency difference or wave number difference satisfies this condition, the evolution of the energy and probability center practically does not differ from the case observed for the monochromatic beam. So in this situation, the flying section reproduces the monochromatic beam. Flying section of the bichromatic beam reproduces the normal section of the monochromatic beam. But with growing frequency difference and with growing propagation distance, certain deviations from the linear evolution can be seen. Here, these deviations is better seen by thin lines, which illustrate the behavior of the energy and probability center coordinates for rather wide, rather strong frequency difference. Here, the line width is about 60 nanometers for the central wavelengths, 630 nanometers. The deviations from linearity become well seen for very wide spectrum. In this case, the spectrum line width is 250 nanometers, and this situation is essentially non-monochromatic, and even the notion of carrying frequency is hardly applicable. But in this situation, except strong non-linear evolution, we can see small difference between the energy center and probability center positions, which is illustrated by difference between thick and thin lines. And remarkably, that this small difference can be registered, can be noticed only for very high frequency difference. These deviations from the linearity are associated with the specific distortion of the flying section, which also can be seen only at very large distances or very large frequency differences. Here, this animation illustrates such a situation. Here, this image beam profile in the initial section stands because in reality it rotates very, very rapidly. So this rotation cannot be seen. This is a stroboscopic effect. But the propagation flying section is deformed. We can see that such a tail appears in the lower part of the image. This is associated with a specific pattern of the bichromatic beam, because both components of this bichromatic beam evolve according to their own frequencies, and they evolve a bit differently, and these discrepancies between them accumulates on very long propagation distances. This distortion of the flying section is better seen in the series of the beam profiles taken at different propagation distances for the flying section. And the flying section deformation is regulated by this deformation criterion, which combines the relative frequency difference or wave number difference and the relative propagation distance with respect to the Rayleigh length. When this criterion is about unity, the deformation becomes visible, and it grows remarkably when this criterion exceeds 2. So far, we considered the energy and probability distributions per se, or indirectly through the energy center and probability center. But now we consider the differences in a whole. This difference can be easily expressed through the slowly varying complex amplitude, and it is characterized by the relative discrepancy between the energy and probability center. This is the function of the transverse coordinates in the beam cross-section. In the spatial distribution of this quantity is illustrated by a series of these images. And one can see that even for rather high frequency difference, the relative difference between the energy and probability densities is rather low, units of persons. And this difference is concentrated near the beam axis, whereas we saw that the energy density and probability density are rather low near the beam axis because the energy distribution is displaced from the axis in this combined model beam. This behavior explains why the relative difference between the energy and probability distributions make so weak effect on the energy center and probability center positions, and they coincide in most of the meaningful cases. Now we are in a position to summarize main results and conclusions of this work. We considered the bichromatic model beam and found that it can be useful for heuristic discussion and understanding of mechanisms underlying the formation and evolution of spatio-temporal light fields. However, it offers a rather coarse and indirect representation on general spatio-temporal fields. First, the model beam is infinite in time and in the longitudinal dimension z, whereas real spatio-temporal wave packets are finite in all dimensions. This model beam is characterized by the spiral quasi-periodic structure both in time and in longitudinal direction, while the model spatio-temporal pulses show rectilinear propagation. However, the periods of the model beam spatial and temporal behavior can be used for approximate characterization of the spatial and temporal field lengths and durations. In the model beam, there is a special flying section which behaves more stationary and supplies a relatively adequate representation of realistic spatio-temporal light propagation. Despite these rather weak possibilities for modeling specific properties of spatio-temporal light fields, the model beam enables some advantages. And for example, it enables an explicit pictorial and self-consistent analysis of the photon probability distribution, whose general description in spatio-temporal fields meets difficulties in the coordinate space. In this way, the bichromatic beam model demonstrates the high degree of similarity between the energy and probability distribution. This conclusion simply supports the known results obtained by Konstantin Bloch, but additionally, this simple model enables to simply analyze and consider quantitative characteristics of these distributions and their discrepancies. The chosen form of the model beam, a superposition of the Gaussian and Laguerre-Gaussian beams, is not unique, and any other two-frequency superposition could be employed, and this freedom allows one to improve the model and adapt it better to any realistic spatial-temporal light fields. And as a side result, we can note that the model beam discussed here can be considered as an expansion of the family of rotating light beams, which was studied more or less intensively some time ago. But in contrast to these rotating beams considered earlier, here the orbital angular momenta of monochromatic beam components are not compensated, and the total orbital angular momentum of the model beam is not related with its visible rotation. And the possibility of controllable rotation of the intensity maximum or minimum or any other characteristic point of the intensity profile with the chosen cross-section permits applications of the rotating line beams for optical trapping and manipulation techniques. Thank you for attention.
Professor Bekshaev, thank you very much for a nice talk. The floor is open for questions and discussions.
Igor Mokhon.
Yes, please, Professor Mokhon.
Alexander, tell me what will be happening with your beam if it propagates with the medium with some physical perturbations?
I suppose this is a quite separate problem, and it deserves special consideration. Normally, beam will experience certain modifications, perturbations, but the details cannot be seen just now.
I see. And you say about only two wavelengths. Can you expand your consideration on the more bigger number of wavelengths?
Surely, this is possible, but my task was to obtain much results by the most simple approach. If you take 3 frequencies, 5 frequencies, and 30 frequencies, we can obtain quite general description, but it will not be so simple.
Oh, yes. We have some difference between 2 and 100 wavelengths. No, so this is my position. And the last questions, what is the reasons you consider it a scalar wave? It seems me more interesting effects appears when we really say about the polarized waves.
The main reason was that the current situation in spatio-temporal light fields is that in many works, the people consider linear polarization of spatio-temporal light fields. Of course, it's not difficult to expand this technique to more complicated polarization states.
Thank you.
All right, thanks very much. Do we have more questions? While you're thinking, guys, I might ask Professor Bekshaev. I might have I didn't notice if you mentioned any assumptions you make on the differences between those frequencies, how close they should be, or there is no limitation.
excuse me, please repeat your question, please.
Two frequencies. Do you make any assumptions? How close are they?
How close? Yes. We take different frequency differences, various frequency differences, and we consider the situation from very close, very realistic, to up to situations which are practically impossible when one frequency is 1.5 times higher than another frequency. So we considered wide range of frequency differences.
All right, I just recall that in some of our nonlinear experiments, our experimental colleagues, invented a very simple experimental scheme how to do it. It just a piezo mirror reflected the second part of the beam. They stay coherent, and the frequency shift was about, let's say, a kilohertz. Would that be sufficient to see anything? This small shift.
You see, it depends on which spatio-temporal light fields we want to consider. And normally, spatio-temporal light pulses, then line width is about nanometer or parts of nanometer, because it depends on the length or duration of the wave packet. If we consider about the pulse, we take kilohertz, we will obtain very long pulse.
No, I meant the frequency difference, kilohertz.
Yes, but if the frequency in our model, the frequency difference is equivalent of the spectral width.
Right. Okay. I see. All right. Thanks very much, guys. Do we have any other questions? Then let us thank Professor Bekshaev for the nice talk, and I think our chairwoman has some announcement about the next talk. Oh no, there is another question. We have time for it. Mark, please go ahead.
So that was just an applause.
Oh, it was an applause. I'm sorry, I missed the sign of it. All right, thanks very much.
Thank you, Alex. Thank you, Alex.
Yeah, thank you, Professor Bekshaev.
Thank you.
And now, may I say some words? Now we have some changes in the program because Professor Wang now has some problems with his health. And we have a small break, and then we start at 3:50 according to the program with the speaker, Professor Marrucci. And then we continue our work with this link, without changes links. Thank you. We have a short...
Because in the program, Claudia, in the program I can see 4 p.m.
3:50 p.m.
Right?
Yes.
Right.
3:50. Thank you.
Thank you very much. We will see you at 3:50 again.
10 minutes for 4, yes?
10 to 4, yeah.
Yes, yes.
Claudia, you may want to stop recording maybe for half an hour before we resume session.
Okay, yes, okay. Mm-hmm.
Hello. Hello.
Professor
Hello.
Marrucci, you ready for your talk? Very good.
Yeah. Yes. The previous speaker was missing because I couldn't see anyone before.
We can see you and we can hear you. All seem
Yes.
to be fine. You can
Okay.
try, by the way, sharing your screen now, and because we had some issues before.
Okay, let me try.
Mr. Chairman, I got the information from Wang that he severely hit his head and he had to go to the hospital, but he will give his presentation maybe tomorrow or the day after tomorrow. Thank you.
Thank you very much. Yeah, we hope
Thank you. Thank you.
nothing serious there.
So do you see my
Yes,
presentation?
we do. We do.
Okay, should I start?
Maybe 1 minute. Well,
Okay.
people join.
Yes, sure, no problem.
Actually, in the PDF that I got from the web page, it says 4 p.m., but maybe it changed.
Pardon? What?
We can start. I see.
It's the time is the official time is 10 to 4 for your so in a minute. Maybe I wait 1 minute and start.
Yeah.
And I have 40 minutes including questions, right?
That's right.
Okay, so let me start. The title is what you see, Photonic Quantum Walk Simulations with Structured Light. Let me start this presentation, if I can change the slide. Yes, okay. By an introduction of basic concepts on what are quantum walks. So quantum walk can be defined as the quantum analog of a classical random walk. A random walk, let's consider only for this presentation, discrete space, discrete time quantum walks, which in a classical case is essentially defined by a random process, which can be described pictorially by a coin tossing, in this case with 50-50% of probability for the two outcomes, and then a walker moving on a lattice. This is why it's discrete space, according to the coin outcome. Now, in the case of a quantum walk, both the coin and the walker become quantum systems. So the coin becomes a coin space, which is spanned by two states, but it's actually a Hilbert space of dimension 2, like optical polarization or spin 1/2. And the walker space is again spanned by an infinite basis of discrete states, which can be, for example, numbered with integers. But again, this is only a basis, so you can construct states that are superposition of these states, as usual in quantum mechanics. So the quantum walk behaves very differently from a random walk. In this pictorial figure, you can see that the walker is somehow everywhere. And this is because in the process of walking is actually defined the probability amplitude of the position of the walker. And the differences, the phenomenological differences with respect to classical random walks are that in the end, you can have interference between different paths that lead to the same position outcome. And the quantum evolution is actually formally deterministic because the probability amplitudes behave deterministically. So true randomness only occurs when the walker position is measured, let's say at the end of the process. The coin tossing process is actually not really, as I said, it's deterministic, it's not really random. It's actually a rotation operator in the 2D coin Hilbert space that I defined. So for example, the coin operator C can turn one side coin, let's say up, into a superposition of up and down, and the same for down. For example, the famous Hadamard operator is described by this superposition with coefficients given by 1/√2. Besides the coin tossing, which is this coin rotation in the quantum case, you need the walker shift operator, and this is coin conditioned, so that depending on the outcome of the coin, you will shift one way or the other. And this corresponds pictorially to this following process. For example, if it's down the coin, then the shift will move it left. And if it's up, it will move right. And such an operator can be described mathematically by the following expression, in which you have the two coin states, projectors, and the translation, non-conditional translation operator T plus and T minus. So the overall evolution can be described as the combination of a coin tossing and Walker shift for each step. So this is a single step. And then an evolution of n steps will be given by a repeated application of this single step evolution operator. The final Walker distribution will be a superposition of many position states, here pictorially described by these cats that have different amplitudes, and this corresponds to different probabilities. So if you look at the probability distribution of the quantum walk and you compare it with the classical random walk, the classical random walk will be a binomial distribution that looks very much like a Gaussian, while the quantum walk typically has a very complex distribution, which is wider and oscillating because of interference. And the distribution width scales with the number of steps in a very different way, because the random walk scales as the square root of n, and the quantum walk scales as n, the width of the distribution. So this was for 1D, but you can have quantum walks in 2 dimensions. And for example, do it with still with a single quantum coin. This can be described in the following way. You have a 2D lattice, as described in this figure, and then a walker that, for example, may start at the origin, and then described by a quantum state, psi naught. And then you apply the coin rotation operator, and then you shift in one direction, for example, x, according to the coin. And then you apply the coin again to the whole state, and then you shift towards the y direction according to the coin, and then you repeat this many times. And this is, for example, a final distribution. So this is the one simple protocol of 2D quantum walk. You can have also other options. This is not the only possibility. Now, why are we interested in quantum walks in general? What they are used for? A possible review about the applications of quantum walks was published a couple of years ago in this paper that I am showing. And essentially, I want to mention the fact that the quantum walks in principle could be used for universal quantum computation. They are actually at the root of many quantum simulation experiments, both of transport phenomena like tight binding models or topological physics. They can be also useful for quantum technologies, and in particular, a quantum walk can be used as a unitary mode coupler between a discrete set of input modes and a discrete set of output modes in a controlled fashion. So this could be useful for certain approaches to quantum computing, such as boson sampling and other options. Now, how do you implement quantum walks with light? The past photonic implementations are mainly based on a variation of a very simple principle in which you have a beam of light or a pulse of light that gets split multiple times by suitable optics according to the coin, which can be polarization, for example. And this can be done in bulk optics or in integrated optics, or it can be done in a longitudinal direction by delaying the pulses in that direction using a suitable scheme like this one. Now, these are all real space description of the walking process. That means that the walker position is actually a real space position of the light, and they all require interferometric stability. Now, let me move to our approach to photonic quantum walks, which we call spin-orbit photonic quantum walks. This work was carried out in Naples by the Naples Optics Group that I lead, together with a theoretical support by the Maciek-Levenstein group in ICFO. The main paper that I'm discussing today, although not the only one, is this paper published in 2020 on Optica, on two-dimensional topological quantum box. Our approach is the following. Instead of using real space for describing the position of the... Pardon?
Ви повертаєтесь спиною до камери і по камері вашу спину показує. Або камеру закрити, або...
There is some background noise, if it's possible to
Dear
stop.
colleagues, can you please make
Ігоре,
sure
ви
that
сідаєте за
everyone is
другий
muted?
комп'ютер, і в результаті вашу спину показує камера.
Okay, try to go on.
Шевелюк, виключи мікрофон.
I'll try to go on. The position of the Walker is described by using a set of transverse modes of a single beam. So we use what is nowadays called structured light. And so we can have a single structured light beam that travels in a single path without any transverse or longitudinal displacements through a sequence of optical elements. And each optical element will apply a certain unitary transformation that somehow encodes the quantum walk. So in particular, for the coin, we use just standard polarization. In particular, we prefer to use circular polarization, that is photon spin, left and right, that will represent the two basis states. And the coin rotation operator can then be implemented very simply by a standard birefringent element, such as a quarter wave plate. A quarter wave plate is actually described by this matrix, which is not Hadamard matrix, but is very close to it. And it can give you the basic concepts. The Walker lattice, initially in our first papers, the oldest paper on this topic was published by us in 2015, was actually based on orbital angular momentum. That means that the Walker states that are described by an integer are actually encoded, physically realized by orbital angular momentum modes or helical modes. However, more recently, we have changed our approach and we use another one which is suitable for two-dimensional Walker spaces, which is based on using slightly tilted waves, or if you want, transverse momentum encoding. So the Walker lattice states, which are described by two integers, mx and my, and define this lattice, are actually described by a set of quasi-plane waves that have a common longitudinal wave vector and an integer number of a certain transverse wave vector along x and y. The transverse wave vector delta k perp is actually much smaller than the longitudinal one, and it is constructed artificially. So it's not intrinsically discrete, but we make it discrete by our apparatus. So essentially, we have in this way two equivalent dimensions, x and y, which makes it a naturally 2D lattice. The lattice constant, as I said, is imposed artificially because momenta are actually continuous, not discrete. And at all these states, despite that they are almost plane waves, they're actually all contained within a single optical beam. So the quantum walk evolution, which occurs in near field, so the diffraction does not has time to separate these waves, all these components remain contained in a single beam. So this is not the same as the standard path or real space encoding that I discussed in the introduction. So you can think of these components of the waves as different components within the same optical beam. And the optical beam is actually then, of course, has an envelope, which is a Gaussian envelope, sufficiently wide that there can be many of these components within it. And in near field, this envelope remains constant. So how do we finally read the Walker position distribution if all the waves are actually contained within the same beam? We can do it very simply using a lens. So the quantum walk process, as I said, occurs within the near field, so that all these slightly tilted plane waves are actually staying within the beam, but then using a lens, we go in the far field, and the far field gives you the 2D Fourier decomposition of the wave, and this will separate these plane waves into separate spots with the envelope that depends on the overall amplitude envelope that you have at the beginning. So notice that in our encoding, the Walker position is encoded in the light transverse momentum in the near field. Therefore, the Walker momentum, which is the conjugate of this Walker position, is actually encoded in the conjugate of the light transverse momentum, which is the light transverse position. So a given position in the near field is actually corresponding in our simulation, in our implementation, to the momentum of the Walker quantum space. Now, how do we implement the coin-conditioned shift operator, which is the more complex element that you need to implement? For those of you who know our older work, for orbital angular momentum lattices that we were using initially, we were using a device named Q-plate that we developed in Naples several years ago, which is essentially a pattern in the liquid crystal cell with a suitable pattern and controlled by refringence using a voltage. But now with momentum lattices, what we use is the somehow linear analog of this Q-plate, which are polarization gratings. We also call them G-plates, but essentially they are polarization gratings. So you have a pattern of the liquid crystal cell in which the optics axis of the pattern follows this kind of structure. So it changes in one direction. If the direction is X, you have an implementation of the coin-conditioned X shift operator. And if the pattern is along Y, then you have the Y shift operator. And the periodicity of this pattern defines the K transverse quantum of the lattice. So, for example, if you have an incoming light beam and traveling through this optical element, the left polarized light will be diffracted toward one direction, and the right polarized light will be diffracted in the other direction by an angle that depends on this periodicity and that we can control. In this picture, they are shown as separate beams, but in the near field, if the beam is sufficiently wide, they will stay within the same beam. So this is the coin-conditioned momentum shift. It's a transverse kick given by this optical element. Sorry. Using these elements, we assemble a 2D quantum walk photonic simulator. This is a pictorial description of this device. It's essentially a sequence of this optical element, and then you have a light beam going through all of them, remaining a single light beam until at the end you have a lens that separates it, and then we map the output in a CCD camera. This is another view in which you can see better what kind of protocol we implemented. Essentially, we have a uniform wave plate that implements the coin rotation. Then we alternate the Y and the X shift. In this case, in this protocol, for simplicity, we didn't have another coin rotation in between. So we have a coin rotation, Y shift, X shift, coin rotation, Y shift, X shift, and so on. This is a photo of the actual setup, illuminated in red because we had, in this example, just a helium red laser going through. And all these bright glasses here are actually our devices with the voltage controllers for controlling the birefringence and giving you this kind of behavior that I described. The whole setup is actually 40 centimeters for 14 steps. In this case, it's 28 elements. And the spacing that we have here is actually limited by practical reasons, about 1 centimeter. But in principle, it should be possible to squeeze this whole setup to a few centimeters, including substrates, or if you can get rid of substrates which have no functional, functional reason except holding the liquid crystal together, in principle, you could squeeze the whole setup into a few hundred microns using, for example, polymeric phase elements. Now, I show you an example of an experiment. This is a 5-step 2D quantum walk based on the approach that I described. This is the experimental data for 0-step, 1-step, 2-step, 3-step, 4-step, and 5 steps. And these are the reconstructed distributions and predicted distributions for the same process. The experiment's theory similarity is very good, 98%, which shows that we are reproducing, at least for a few steps, fairly well the process. This is a better image of the final distribution after 5 steps. This is the actual size. You can see it's everything in a few hundred microns. And each of these dots, as I said, initially is a single plane wave mode, quasi-plane wave mode within the optical beam. And in this case, we address about 120 modes in this way. Let me now show you a more recent experiment in which we use the same concept for doing measurement really in quantum domain, because the previous experiment was actually in the classical domain. So this work was done in Naples in collaboration with Sapienza's group in Rome, led by Fabio Scerrino, and was published last year. And essentially, the concept is the same I already described. This is the setup. The quantum walk implementation is just a sequence of optical elements in 2 dimensions here. And what changes, since we have to deal with individual photons or photon pairs, is that we need a generation of photons, which was done by standard spontaneous parametric down conversion using BBO. And then we have the 2 photons going to 2 optical fibers. And we did experiments in which 1 photon was just a trigger and the other photon was going through the setup, or both photons went through the setup. And then at the detection stage, we needed single photon detectors, which was done by using a fiber array, 2-dimensional fiber array, which connected each spot to be detected with a separate APD, avalanche photodiode. And then we had the electronics for coincidence. So let me show you a couple of results. This was a sequence of 3 steps with a single photon, which was triggered by the other photon generated in the spontaneous parametric time conversion. These are the theoretical distribution that you expect after 3 steps, and these are the experimental ones, which is in relatively good agreement, although not perfect, as you can see. And with photon pairs, 2 photons are crossing the setups. And what you see is actually the correlations. And the correlations are shown here by depicting an index that somehow encodes both the positions of the 2 photons, actually both the coordinates of the 2 photons, of 1 photon and the other photon, so that in the single diagram you can see the correlations between the 2 photons. So this is after 1 step, 2 step, and 3 steps. And again, you can compare theory and experiments, and you can see that they are sufficiently similar. So this was done in the quantum domain. Now, in the final part of my talk, I want to show you our latest work, which was aimed to realizing very long photonic quantum walks. So far, what I showed were quantum walks on only a few steps. And the problem with making very long quantum walks is the following. If you want to do a very long quantum walk, you will need a lot of optical elements, which is, of course, costly in terms of realization. And also, each optical element will introduce optical losses, and that makes it not very efficient, so because it will reduce exponentially the final number of photons that go through the whole setup. Even if you realize the same setup using a loop architecture, so that you only need one optical element for the single step, and then you go through it many times, still the optical loss problem will remain. So this makes the whole process not scalable, and this is particularly important in quantum applications. If you have multiple photons going through the setup, everything scales also as the power of the number of photons, which makes it even worse. So what we thought to do is to try to compress the whole unitary evolution into a single or a few optical elements without having to have the same number of elements as the number of steps. So essentially, the concept is to squeeze a number n of elements into one or few. So let's discuss again the whole optical evolution, for example, of this setup. Each unitary operator U corresponds to 3 of these optical elements, actually, a quarter wave plate and then the 2 polarization gratings, one along Y and one along X, and then you repeat it many times. What you want, so what you have at the end, usually for an n-step optical evolution, is the power n, the nth power of U, where U is the operator. Now, consider the following. If you have a narrow beam of light that goes through the optical elements only at a given position, then you will have that the polarization that you have at the beginning, or if you want the quantum state that you have at the beginning, will undergo this evolution, but will remain in the same position the whole time. So at the end of the process, you have this operator U applied to the initial position and somehow parametrically dependent on the position. If you repeat the same thing at different position, you have the same behavior. So somehow the position in this evolution, since the whole process occurs in the near field and diffraction can be neglected, is conserved. Light position is conserved, doesn't change the transverse position during evolution. This corresponds to the fact that in the Walker space, the momentum of the Walker, which, as I told you at the several slides ago, is actually the same as light position, is conserved during evolution. The Walker momentum is conserved because what we are describing are phenomena, processes, which are actually translation invariant. Therefore, since they are translation invariant, the momentum is let's say, a good quantum number, commutes with evolution, and therefore is conserved. Now, each element of the sequence is just a local polarization manipulation. So each U can be described by SU2 matrix that changes the polarization in the Jones formalism. Therefore, also U to the n is actually just SU2 matrix that describes a polarization transformation. It's only much more complex in the dependence on X and Y. So this means now, since SU2 Jones matrix can be implemented by using only 3 wave plates, and in particular, a simple approach is to use a quarter wave plate, followed by a half wave plate, and then another quarter wave plate. If this quarter wave plate, half wave plate, and quarter wave plate are uniform, by determining their optic axis orientation, you can determine the Jones matrix, and you can create any SU2 Jones matrix. That means you can do any polarization transformation. Only the global phase is not controlled. If you add another wave plate, you could control also the optical phase if you want. Now, if you make the optic axis of each wave plate space dependent, space variant, as shown in this slide, then the optic axis orientation is a function of X and Y. Therefore, the Jones matrix that you realize is a function of X and Y. And in principle, you can use this approach to give rise to a Jones matrix that creates the same effect as the whole process UW operator. Now, how do we make these space-variant waveplates? The approach that we follow is always the same. We make patterned liquid crystal cells, as shown in this picture. And the patterns that we have designed are not simple grating or simple azimuthal cuplates as before, but much more complex. But they are artificially designed, and this is why we call them liquid crystal metasurfaces, because they somehow have certain analogies with metasurfaces, although the structures are not sub-wavelengths. And we realize them by using scanning photoalignment, which is the same technique that we use actually to manufacture cuplates or manufacture polarization gratings. And so the ultra-long quantum walks in the end can be encoded by using 3 of these, let's say, liquid crystal metasurfaces. They will generate the same optical evolution. Now, let me show you some experiments. We first did experiments just in 1D, therefore, and this was a work done in Naples, so in collaboration with a theoretical group in ICFO, in this case, Pietro Massignan and Alex Duffin. And the experimental setup is very simple. We had the laser, we collimate it, and then we go through these 3 metasurfaces, and then we use a lens to extract the information about the final distribution. For simulating a 20 time steps evolution, we had to realize these 3 quarter wave plates, half wave plate, quarter wave plates, with the optic axis distribution that is color encoded here, with this color encoding shown here. And the pattern is only 1D because we had only 1D quantum evolutions in this case. And so in the end, we have an image which looks like this with several spots. Let me make it larger. So this is the final distribution, and this is the corresponding probabilities calculated from this distribution, compared with theory. Blue is experimental, let's say red is theory, and there is a similarity of 93%, which is fairly good. And this was realized, 20 time steps realized only with 3 optical elements. Then this is what one of the 3 metasurfaces that you need to realize at 240 time steps. And this is the corresponding distribution. Blue is experiment and red is theory. And here we are somehow realizing a 240 time steps process just with 3 optical elements. And the similarity between theory and experiment is 86%. By the way, this span of modes, including also polarization, addresses 400 modes, discrete, separate, orthogonal modes with a single device. We also started working in 2D, and this was work done in Naples by this co-worker of mine. The paper is not published yet. The experiment is based on the same setup as I already have shown, except that the optical elements are now patterned in 2D. So the liquid crystal metasurfaces have a structure in 2D, which is shown here. These are the patterns that we realized for 3, 5, and 10 steps. The pattern of the first, second, and third waveplates. You can see that the structure of the pattern become increasingly more complex and more highly resolved by increasing the number of steps, which is the actual ultimate limit that we have in realizing very long evolutions. Because if you increase the number of steps very much, then the resolution needed to realize the liquid crystal metasurfaces become not accessible experimentally, but in principle possible with other methods, with other techniques. And then using these waveplates, so this is a photo of one of those waveplates, realized experimentally. This is seen between cross polarizer to show the birefringent pattern. And this is an experiment of a 10 steps quantum walk generated using this approach. Again, this is the measurement. The second column is the measurement. The first column is the simulations, then reconstruction, and compare with the theoretical distributions. In this case, despite we are only making 10 steps, we are already addressing 800 modes, because the two-dimensional systems have a much larger growth of modes with the number of steps, much faster than growth of modes. So I'm coming to my conclusions. We have demonstrated new approaches, new platforms for implementing 1D and 2D quantum walk simulations using light, using a single optical beam, which is good because you don't need to have interferometric stability. So it's, let's say, experimentally simpler to implement. We use them to study topological physics, although I didn't discuss these simulations and this physics today. Then we developed a technology for simulating very long quantum walks using only few optical elements. We demonstrated more than 200 steps in 1D and 10 steps in 2D with minimal losses. And this can be possibly useful for control coherent coupling, possibly also switchable, because this liquid crystal optical element can be switched on and off of several hundreds or even thousands of well-defined orthogonal optical modes. And this could be potentially useful for photonic quantum technologies in the future. And thank you for your attention, and Slava Ukraini.
Heroям Slava, and thank you very much for a very nice talk. Colleagues, we have time for a few questions and discussion. Guys, I cannot see if you raise a hand, so if you have a question, you can just unmute and start talking. All right, I have maybe a general question to Professor Marrucci. What do you think? How is there a question? No? Professor Marrucci, how do you think? How far is you developed already kind of devices, and how far is that from a patent and technological implementation? Do you think it's a long way from fundamental studies?
Okay, for patent, it's not a long way, because we patented some of our work, so it's not a problem of patent, of course, but real technology applications, I cannot really tell. It will depend a lot on which technologies becomes more dominant for quantum processing applications, because if the dominant technologies becomes mainly optical photonic technologies, then I think we can have some chance to being useful there. But if they will stay mainly in the superconductors and so on, then maybe not. Of course, there are still applications in the field of communication, and even communication between nearby, for example, chips can be more efficient optically in data processing. So there are possible applications there that we can look for, but I think we will know in a few years.
How about it in terms of stability? When you scale it to
stability, you mean in terms of
device
results?
Stability when you build it, and
first of all, our schema is fairly stable. As I said, it's not interferometric, and hence is already stable in itself. And as I said, if you need something which is not too flexible and has to reproduce always the same thing, you can even think of realizing it in a technology that can be as compact as a few centimeters or even millimeters.
That's
so
what
that
I-
would make it extremely stable, but you lose flexibility, of course. So it's a matter of the final applications that you really want. If you need something that calculates always the same thing with changing only the input, but with the same processing in between, then it can be very convenient. So maybe I can stop sharing my screen. Okay.
All right, I think that it's my turn now, right?
Yes, I was just inviting Professor Shevchenko for the talk, and my Zoom was interrupted. Sorry about that.
Okay,
Yeah.
nice seeing you.
All right. Professor Shevchenko with invited talk on aberration-insensitive coherent and incoherent optical imaging systems. The floor is yours.
Let me share the screen. Something is wrong. Let me see. Yeah, I did not open yet there. Just a second. I hope you see my screen, right?
Yes, we do. Yes, we do. All good.
Oh, it's full screen. Right. So thank you very much for the introduction. I just have to add that I work in the optics and photonics group in the Department of Applied Physics at Aalto University. And on this picture, you can see the central railway station of Finland. And I think that we all understand that now the most important thing is the victory of Ukraine, of course. And back to my presentation. Somehow I cannot make it. Cannot return it back to the previous slide for some reason. Just a second, I'm sorry for this. What should I try? I'll try. I start again. Now it works. Okay, here is the outline of my presentation. Please tell me if you hear me and see my slides.
Yes, no problem. It's all working. Thank you.
Thank you very much. Right. So I will start with some examples of aberration-insensitive imaging systems that exist, and then I will show our interferometric ghost-like imaging system that is based on the field interferometry rather than the intensity interferometry. I'll show two microscope setups for transmissive and reflective amplitude and phase objects with the experimental results. Then I'll consider defocus insensitive imaging system that builds images of Bessel beams. And finally, I'll show an approach where spatial phase modulation is used to obtain a defocus insensitive imaging system. The final slide will be about I will draw some conclusions of our work on this topic. So, first of all, I will not speak about aberrations of optical imaging systems, such as aberrations caused by spherical lenses or something like this, because they can be corrected by redesigning the optical components. But I will speak about some aberrations which cannot be compensated for by redesigning an optical component. As an example, you can see in this picture a microscope where we want to see something behind an inhomogeneity in the refractive index of a specimen. So if you want, if the refractive index contains some inhomogeneities over here, then light will be the wavefront will be deformed. So if you eliminate the sample by a collimated beam, then the inhomogeneity in the refractive index will make the wavefront deformed, not spherical, and the aberrated focal spot will be large, and its shape can be whatever. And if this is a fluorescence microscopy, then you pump all the molecules around and you get the fluorescent light that propagates back and becomes even more aberrated, so you don't see anything sharp enough. And the way to get rid of the aberrations would be, for example, to use the adaptive optics tools. You can use a deformable mirror, as in this picture, to pre-deform the wavefront in such a way that on the way through the inhomogeneity, it will become, the wavefront will become spherical and the corrected focus will be diffraction limited. Then in this case, the scattered light or the light produced by fluorescence will propagate through the same source of aberrations, and the deformation will be compensated for by the shape of the deformable mirror. So you will have a plane wave that will be focused perfectly with your ocular lens of the microscope. So this is what you can do, but and the results are quite good. Here are the images of taken by multiphoton microscopes. It's either fluorescence microscope, and for example, this one is these images are taken by a microscope working at the second harmonic, and you can see the picture before correcting the aberrations and after, and the aberration correction method works well. But if the aberrations are very complex and strong, and if they change in time, that it's difficult to use this technique. And it would be nice to have an a priori aberration-insensitive imaging system. And I will show some examples of such systems. The first of them is a classical ghost imaging. So probably you all know about this technique. It came from quantum mechanics, where people use it in tangled photons and calculated their coincidence and obtained the images from the coincidence detection. But then later it was realized that also the intensity correlations can give the same results, and that's why it's called classical, not quantum. So the simplest imaging system working on this principle is shown over here in this picture. So what you use, first of all, you need a spatially incoherent illumination light. You can make a spatially coherent laser beam spatially incoherent by transmitting it through a rotating ground glass. Then the ground glass will make will cause intensity, phase and intensity fluctuations, which will be such that if you take 2 points in the transverse cross-section of the beam, they will not show any intensity correlations. So now you divide the beam into 2 parts. In one part, you have your object, but then after the object, you have a bucket detector with no resolution. In the second arm, you have a pinhole that is scanned over the cross-section of the beam, and then the electric signals coming from the bucket detector and the pinhole detector come to a correlator, and you plot the correlation function as a function of the coordinate of the pinhole. And then you can see that the reference arm did not see the image, the object at all, and the object arm is such that you don't have any resolution, and you are still able to retrieve the image. And in this case, just because this detector is a bucket detector, you can have any aberrations between the object and the detector, and the imaging system will be fully insensitive to the aberrations. Then, if you replace the rotating ground glass with some with some spatial light modulator, namely some phase modulator, with deterministic patterns there, then you know what to expect, and you can correlate. So we can remove the reference arm and just correlate the obtained electric current with the pre-computed electric current that depends on the pattern in this spatial light modulator, the phase profile. And in this case, the system is called, the approach is called computational ghost imaging. You can also use some lenses if you want to have some magnification, as in like in this picture. So the setup is the same as this one, but you can project the field to the pinhole detector using a lens too. So these experimental setups are explained in this and this in these 2 papers that I cite. Let me take some laser pointer, maybe it will be better. Right, but the resolution of these imaging systems is limited by the size of the speckle. So you cannot easily get a high resolution. It's quite difficult to implement such a system. Another imaging approach that is potentially aberration insensitive is the single pixel imaging. There are 2 main types of single pixel imaging. In the first, in this system, you create a structured illumination light, and then you have a single photodetector, single pixel photodetector, collecting the overall intensity scattered by the object. And in this case, you make an image on a DMD, that is a digital micromirror device, and then you use a set of patterns of the device and measure the intensity. So it's quite close to the imaging system over here, where we use pre-computed patterns and can calculate the correlations. There you can have aberrations. In this case, whatever aberrations like turbulence, find something like this between the photodetector and the object. In this case, between the image and the photodetector. But if you have any aberrations on this way, then they will cause they will somehow influence your image. So this is a drawback of this system. You can also have the so-called lensless single pixel imaging, where you have a mask where you can change the pattern. So it's an assembly of apertures. and measure the total intensity at a single point. And this imaging system is called aberration-free because it doesn't contain any lenses that can introduce aberrations. The aberrations in this case can be between the apertures and the detector. All right. Here is another lensless ghost imaging system using a Mach-Zehnder interferometer, but in contrast to ordinary ghost imaging systems, which work on, which use the intensity correlations. Here, the field interference is used rather than the intensity interference. So we have two arms, and the transparency is the object that you want to measure the image of. And in the second arm, you have a long rod of glass, and you tune the system in such a way that the pattern corresponding to the position of the sample corresponds to the length of this arm. So they can correlate. So the field from the reference arm, from this arm, can correlate point by point with the field at this position. But after this position, you have light propagates ahead, and the diffraction in principle destroys the information about the distribution, the spatial distribution of the object. But because you have spatial incoherent illumination light, only the points that correspond to the points of transmission in the transparency over here will produce interference, some interference. And then if you use two cameras, then because of the phase shift introduced by the beam splitter, or you just shift a little bit the camera in such a way that you have the so-called phase reversal images by the two cameras. Then you can subtract the image of one created by one camera from the image created by the other camera, and the image of the object will be retrieved. So in this case, the signal to noise ratio and the resolution of the imaging system are not easy to control. The aberrations can be here, of course, and they will not influence the quality, much at least, of the images. And this is one more existing full optical imaging system that allows you to reduce optical aberrations, and the technique is called the full field optical coherence tomography. You know that in a classical optical coherence tomography, you have a single beam that is scanned across in the transverse plane in order to retrieve a three-dimensional optical image. And for that to be possible, you need light with as short as possible longitudinal coherence length. So it must be somehow broadband optical source for the illumination. But here you don't need to, this system is better because you don't need to scan a focused beam across the sample. You obtain the whole picture of a transverse profile immediately, but you still have to have a short longitudinal coherence length in order to have the longitudinal resolution too. The system is shown over here. You have a spatially incoherent light once again, and then the beam is reflected by a mirror, by a semi-transparent mirror towards the sample. But then after the objective, you have a polarizing beam splitter that splits the beam into two parts. One is just reflected from the mirror, and this light is the reference light, and the other one is focused into the sample and scattered from a focal plane roughly. And you will get then the two beams are combined on the way back by the polarizing beam splitter. They have orthogonal polarizations, but they propagate through a photoelastic modulator that modulate only one of the polarization components. So it is equivalent to phase shift in one of the polarization components. Then, because you want to see an interference fringe pattern, you use an analyzer that is a polarizer rotated by 45 degrees or some other angle. And this polarizer makes the two components interfere, and you have an interference pattern observed with the CCD camera. And each time you have something like this. It's an interference fringe pattern. Then when the phase is modulated, the fringes move, and you can retrieve, you can extract only the interfering parts of the image and get of this pattern and get the interferometric image. And just because you use spatially incoherent light and you don't have any aberrations there, you can reduce all the aberrations for light on the way from the beam splitter to the point from which you want to get the information. So then you just move the mirror along this direction, and slice by slice obtain a 3D image of the object. And of course, for this 3D imaging, if the object contains some inhomogeneities of the refractive index, then of course it's important not to have the aberrations caused by them. And this is possible just because you have the spatial incoherent illumination. But in the system like this, the longitudinal coherence length is small, some microns. So if the aberrations are too strong, shifting the wavefronts by more than 1 micron or more than the coherence length, then you cannot retrieve the image because you will not see the interference corresponding to the correct distance along the z direction. So we wanted to construct an imaging system that is insensitive even to very strong aberrations. And this is the first system that we have built. It's based on a Mach-Zehnder interferometer. We use a spatially incoherent light as well from an LED with a large emitting area. So we collimate the beam, then we have a beam splitter to split the beam into the object into two. One is the object beam and the other is the reference beam. Then because we wanted to construct a microscope, we have 2 microscope objectives, and the sample is in their common focal plane. Then after that, we have some mirrors there and there, and the two beams. Also, we have the same objectives in the second arm because otherwise the image will be flipped, or the pattern of the, how to say, this beam will be flipped around one of the, so it will be inversed kind of, and we will not be able to see any interference. So the arms must be identical. And then we have a beam split, polarizing, or maybe normal beam splitter. So one of these beam splitters is polarizing beam splitter, the other is not. But then we have a polarizer at the output in order to tune the relative intensities in the two beams. And then we have a bandpass filter with a narrow transmission band. It's we use it about, so the transmission band is about 1 nanometer wide, which corresponds to the longitudinal coherence length of 0.4 millimeters. So the aberrations can be strong, such that the wavefront can be shifted by some fraction of a millimeter. Then we so we have 2 mirrors instead of 1 mirror over here and over there, just because if now you shift these mirrors along the arrows shown in this picture, then this beam does not move. we just increase the length of the arm without moving the beam. So we move these mirrors, and as a result, the interference fringes move in the interference fringes observed by the CCD camera move, so that every pixel sees a sinusoidally varying intensity. And then a computer just calculate the maximum intensity minus the minimum intensity, and this gives us the image of the object. Even if we destroy the normal intensity image with the diffuser, as this D is a diffuser. So, and the diffuser that we used, it was just a tape, so we can see nothing through it. And still we were able to retrieve quite good quality and high resolution images. And to explain how it works, I have this picture over here. So the sample arm without the aberrations, if I block the reference arm, okay, then I have only the sample arm. It's a normal microscope. And if the object is just a pinhole, then my camera will see a spot that corresponds to the point spread function of the system. If I have the aberrations like this, then the point spread function will be large and deformed, like shown in this picture. But in the reference arm, we don't have any aberrations, so we have the area of light that can interfere with this light of the size of the point spread function. And this is a coherence, roughly speaking, coherence area of our beam. So then when both arms are open, the fields overlap and we have some interference within the size of the point spread function. Then the computer calculates the maximum intensity minus the minimum intensity at each pixel when this mirror moves, and we get this image. In the presence of aberrations, we still have the interference fringe pattern within the coherence area of the reference beam, in spite of the fact that the point spread function of the corresponding to the second arm is so large. Therefore, when we move the mirrors, only within this spot, this little spot, the intensity changes. The static intensity is just removed by this operation, and we get the same point spread function there as in the absence of aberrations. We can also measure the retrieve phase objects as well. Here is the picture. If you have a phase jump somewhere, then after doing all what I have just described, you have a dark line along the phase jump of the width that is approximately equal to the width of the point spread function. Now the experimental results. So this is a transparency that we use it. The object. This is the this A is made of a stripe of gold on glass, and the thickness of the stripe is about 20 micrometers. Sorry? I don't hear anything for some reason.
Continue, please.
Okay, okay. Right, thank you. So here we just shift the sample from the focal plane of the objective, and this is what we see in the normal intensity image when the reference arm is blocked. Then we open the reference arm and proceed as I explain it and retrieve the image. And the image is quite good. Those dark lines are the stripes of our light emitting diode. It's the surface of the light-emitting diode that we use. In this case, we just destroy, and here we the A is made of slits in an opaque gold film. So we insert a diffuser, and then the image is destroyed. Then we open the reference arm and retrieve the image. And this is a phase object. It's a surface relief pattern. You can also see that you can retrieve it. When you introduce, when you put it, when you inserted the diffuser there, like, the image looks absolutely hopeless, but still the interferometry gives you the object. This is some mathematics. I will probably not go through. It's quite simple, but maybe not very entertaining. But the main point here is that if you don't have aberrations, then the image is given by convolution of the transmission function of the object times the squared absolute value of the point spread function. And when we have aberrations, then in this integral, the aberrated point spread function becomes so large that we can remove it from the integral, and then the retrieved image is given by the convolution of the absolute value of the transmission function and just the absolute value of the point spread function. So we lose this square over here. So the resolution is not as good as without aberrations, but quite close to that. Also, a phase object can be shown that is given by convolution of the phase jump with just the absolute value of the point spread function instead of a squared absolute value of the point spread function. We have also created an imaging system to observe reflecting objects or backscattering objects. We just replaced the Mach-Zehnder interferometer with the microson interferometer. And the reference arm is here. We move a little bit this mirror, and then the interference fringes start to move within the place and where they are observed, and then we calculate the difference between the maximum and minimum of the intensity at every pixel and retrieve the image of the object. And you can see that if you introduce a focusing error, then you don't see anything, and then you retrieve the object. And with the diffuser, we also get some improvement, and also phase objects can be obtained. And this is a promising optical system for maybe biological specimens. If you want, if it contains some inhomogeneities in the refractive index, and you want to see what is behind the inhomogeneities, then you can improve the quality of the image. Now now I'll explain another optical system where we wanted to get rid of the aberrations, call it defocus. So roughly speaking, if you have a microscope with an objective and an ocular lens, then you have a specific, and if the microscope objective is infinity corrected, then you want the object to coincide with the focal plane of the objective. And then if you shift the focal plane, the sample from the focal plane, you introduce a defocus, which is an aberration, and the image is blurred. Or you just don't see the image; it's washed out by this aberration. So we wanted the image to be sharp and independent of the position of the object along the optical axis. And the idea is to use Bessel beams instead of normal focused beams, because Bessel beams do not diverge upon propagation. If the image is made of Bessel beams, then it should be independent of the position of your detector array, right? And by reciprocity, if you fix the detector array, then the image must be independent of the position of the object. So this is interesting because you can see three-dimensional objects quite sharp. Here I just show the intensity profile of Bessel beam of a zero order Bessel beam. It's quite well focused with the intensity that is quite high compared to the intensity in the side rings. And the Fourier transform of a Bessel beam is a delta function that is plotted over here, just a ring with the radius equal to the transverse wave number for the Bessel beam. So if you want the image to be composed of Bessel beams, you should insert a ring-shaped aperture in the focal plane of the second lens, in the front focal plane of the second lens. Then any point, for example, the point P here will be diffracted by the slits of the ring-shaped aperture. It will spread and form a Bessel beam over there. And this must extend the depth of field of the system. So we have calculated the properties of the system and found them to be as follows. So the length of the Bessel beam cannot be infinite because the length is finite. So the length of the Bessel beam depends on the radius of the lens. Then the transverse resolution is even improved compared to the case when you remove the obscurity from the ring, right? So without blocking the central part, you have 0.61 lambda over the numerical aperture of the lens, and in the first case you have when you block the central part, you have 0.38 lambda divided by the numerical aperture. And the numerical aperture, if you want to have the resolution in this plane, then the numerical aperture is given by the radius of the ring divided by the focal distance of the objective. Okay, but due to the side lobes of the Bessel beams, you can see that the intensity is not zero around. The background light intensity is increased, and the transmittance of the system is decreased because you block the central part of the beam. And so we did our calculations, then we started to do the experiments, and we noticed that when the illumination light is spatially coherent, the system does not work. For example, this is what we observed when imaging a ring like this. And then we calculated and we obtained the same result. And those fringes, those interference rings, they come from constructive interference between the Bessel beams that form the image. So the interference, the side lobes of Bessel beams interfere and produce this garbage. So in order to get rid of it, we need the Bessel beams not to interfere with each other. And the solution is to use a spatially incoherent light. So we switch it to a spatially incoherent light, and we obtained very, very good images, which do not change when you shift the object along the optical axis. But we have some background around. And then another drawback is that that we have low transmittance and actually low contrast because of the background light. Here you can see what happens if you don't have it, if you don't block the central part. Then the image is just washed out when you shift the object. But if you have a ring-shaped aperture, then the resolution is the same, independent of the position of the object. but the contrast is not as good. But you can improve the contrast just computationally and get quite well images. Still, we would like to increase the transmittance of the system and increase the contrast. And the idea here was to replace the ring-shaped aperture with a phase mask. And we wanted just to see if a computer optimization algorithm can give us some phase profile that will produce non-divergent optical fields at the output. And we did this, and this is one of our results, current results. So this would be a profile. If the face mask is made of glass, this is the height, right, of a glass surface. So you have a phase shift and this is the radial distance, right? So we have a phase difference. It's quite flat. The phase profile is quite flat at the center, and then it starts to the phase starts to be shifted closer to the edge of the aperture. So with this mask, you can have the field between the mask and the lens looks like this. When the point is on the axis, and when you shift the point from the axis, it looks like this. And those two lines are obtained for a point on the axis of the system. And this one is an image of an off-axis point. And notice that the image is stretched in this direction by a factor of 10. You see it's from 0 to 1 millimeter, and here from 0 to 10 millimeters. So and they're quite nice, very, very narrow beams. They are not Bessel beams, but they look a little bit like Bessel beams. And if you would have a Gaussian beam with the same diameter, its relay range would be only 1 millimeter. So you even see that the improvement is quite significant. These are people who worked on all these topics. Elena is from Dispelix, from a company. Markus Neumann is one of our former PhD students. Now he is in Karlsruhe Institute of Technology in Germany. Thomas Sturgis, from the Institute of Theoretical Solid-State Physics. Professor Matti Kaivola from our university, Tero Setala from the University of Eastern Finland, and our PhD student, Pano Hilden, and an undergraduate student, Kauri Palsi, was a summer worker this summer, and he worked on the optimization of phase profiles. So these are the conclusions that I would like to draw. First one is that severe aberrations can be removed by interferometric methods when using transversely incoherent and longitudinally highly coherent illumination. The depth of field can be considerably increased by composing the image of mutually uncorrelated non-divergent beams, which is possible when using an incoherent illumination. And these methods can be used for high-resolution aberration-insensitive imaging of extended three-dimensional objects, including biological samples. By this, I finish my presentation, and thank you very much for listening. And if you have some questions, please ask.
Thank you very much for a nice presentation. We do have time before we close the session for the questions or comments, discussion.
I have a question.
Professor Mohan, please.
Yes. Can I see the slide where you say about the Bessel beams, where you...
This one?
Oh, here.
Yes.
Here we have a deep minimum, yes?
Sorry?
Here we have a deep minimum, 0. In the center of the
Yes, in the center of the mask.
And you say that this is the transform of this distribution.
by introducing a ring-shaped aperture, when we make the beam on the right-hand side from the lens.
Okay, but the diffraction pattern from the ring have a maximum in the center.
Yes.
This is
Yes, it is. You see, this is the maximum.
how and how you can write this one. I don't understand correctly.
So this is a truncated Bessel beam with, roughly speaking, this profile, this transverse profile. So the intensity is just squared function. It's the squared zeroth order Bessel function over there.
Okay, thank you.
So the diffraction, probably you wanted to. So if you want to see the iris spot or the Poisson spot, you can see them there. You see, those are the central spots of the diffracted light. But then with the lens, you don't have any modulation. You have just a Bessel beam there.
Okay, thank you.
Thank you. Please, any other question?
Maybe I can ask a question.
Yeah.
Yeah. Very nice talk, Andrei.
Thank you.
So you first analyze this ring mask, and then you do your face mask. Suppose that another advantage of the face mask is that that is much brighter because you're not throwing away a lot of light.
Exactly. This was the whole point. This is why this is the main reason of why we started to do that. But I just honestly did not believe that we will get any face masks that would do what we see. And this was very surprising.
So, I was going to ask, do you have an estimate of the ratio, how much brighter the central thing is with the mask and with the ring? I guess with the ring depends on what radius you use for the ring, what thickness.
With the ring, yes. If you want a perfect Bessel beam, then the ring must be infinitely narrow, so no light is transmitted. But with the face mask, you see that the variation of the face is quite smooth. So almost all light is transmitted.
Okay.
Small comment. It seems to me that the analog of your face mask may be implemented as a combination of two computer-generated holograms. The simple ring, but inside this ring we have the grating with the shifted fringes.
Exactly. Yeah, this is what I expected, because our computer just generates, it starts either from a flat face profile or from a random face profile, and then the computer starts to to maximize the figure of merit, and then when it stops maximizing, when I look at for the first time, I was surprised because I thought that the computer will give us exactly what you said, a diffraction grating that blocks light from the central part. But we didn't see any. Look at the face profile; it's so smooth.
Thank you.
So just one quick follow-up. So you have here the face. Well, the face is, you have it as a height.
Yes.
What does it correspond in phase, this variation?
First of all, I have to say that we did not yet get the global maximum for our figure of merit. And the computer program finds all the time some local maximum, and the profiles are all the time different, right?
I see.
But in this particular case, it's about 2 pi, the difference.
Okay, 2 pi. Wow.
Yeah, between the maximum and minimum.
Okay. But the maximum being at the edges, those spikes.
At the edges, yes.
Okay, so it's about pi between the
Maybe
center,
pi.
let's say.
Yeah,
Yeah.
about.
Okay.
But we have obtained many, you know.
Sure.
And this is so we just we have to continue working on this and find some. I believe that there should be like the perfect face mask for that. And of course we tried also binary phase grating. That is radially symmetric, circular symmetric.
Yep.
We tried that too, but the results are not so good yet.
Okay. All right. Thank you.
Thank you.
Nice discussion. Thank you very much. Let's thank our speaker again.
I just want to add before I leave that the ideas came from Miguel's papers and the presentation. At some point, Miguel has a nice theory about how to make arbitrary fields divergence free, and this is what inspired me. Okay, thank you again, and I stop sharing.
Thank you very much. Let's thank all our speakers. That is the end of today's session, and we will see you all tomorrow morning.
Thank you very much, heroes of glory. I thank you for your contribution. Today's session is closed, but in 10 minutes, will be a poster session where you can take part as well. Welcome. Thank you. See you tomorrow with a singular optics session which start at 9 o'clock. Thank you.
Thank you very much. See you.